Okay, thank you. Uh, I'll begin with thanking the organizers, Manoj and Anasan Sastry, for organizing this wonderful workshop and conference. I've been enjoying every bit of the workshop and plus conferences, the discussion meeting as well. Uh, so, okay, it's quite interesting to see that still people are there for the last lecture. Thanks to Sastri Garu. Okay, uh, so let me first write the title of my talk. Conjugacy classes of centralizers in algebraic groups. So let me begin with definition. So let G be a group. Two elements X and Y in G are said to be G conjugate if their centralizers are conjugate in G. For some T in G. So it's easy to see that it's an equivalence relation, and this forms equivalence classes. And this relation is denoted as X, Y, and we put Z below. And the classes are called G classes. So I am interested in understanding these classes. Uh, so it seems like there is a relation with conjugacy classes. So let's quickly see that. So if X is conjugate to Y, then X is G conjugate to Y. That's very easy to verify. So, however, this is only one way. In general, it's not true the other way around. And the general question is to understand G classes. So, the parameterize G classes in a group G. And this is generally different from, it's a weaker condition than conjugacy. So let's see quickly some example, some very small example given that we have learned gap. So what happens in abelian group? So here conjugacy classes are of size kind of single elements. So there are as many conjugacy classes as number of elements in the group, size of G. What happens to G classes? So centralizer of every element is whole group, so there is only one G class. Another interesting example to keep in mind, let's look at GL and K. Let's look at only certain elements here. So for example, I want to look at diagonal elements. So this example we have already seen earlier in workshop. So suppose I take this diagonal element, lambda 1, let's say n1 times, and then lambda 2, let's say this is n2 times, and so on, and then at the end, let's say lambda r this is nr times. Let's say my this is my element x in GLNK. This is diagonal element, so it's semi simple. If I compute its centralizer, this computation we all did earlier. So this will be GL1, GLN1, GLN2, and GLNR. So if I take different elements of this form, where lambda i's are distinct and different lambda i's, then they are not conjugate. However, their centralizers are going to be same. So all these elements of this form, as long as you have this lambda is distinct, they are going to fall in the same conjugacy class, same G class. So all these elements form one G class. Another interesting example, just to keep in mind, let's look at our group Q8. So what are the conjugacy classes here? So you can see the conjugacy classes are going to be right. And what are centralizers here? Rather, let's write G classes. So the elements 1 and minus 1 will belong to one class. What about other elements? So it's the same as their conjugacy class. I want to point out here in this particular example, I wrote this example kind of deliberately. If you look at the centralizer of element I, Q8, this is plus minus 1 plus minus I, and centralizer of J in Q8 is going to be plus minus 1 plus minus J. So you see that these two subgroups in Q8, they are not conjugate, even though they are isomorphic. So when we compute, you don't have to kind of get carried away that if you see two things are isomorphic, then probably they are same G class. So that's the reason why I wrote this example. Okay, so let me write down yeah. Yes, would not be okay. Yeah. Okay, so let me tell you a little bit of motivation why we study this problem. So first motivation comes from geometry, groups acting on manifolds. So among many things, I'll just point out one interesting theorem. So this is theorem by Mostow, 1957. So here we are interested in studying, let's say a Lie group, or let's say Lie group acting on a manifold M. And then here you define a stabilizer of an element here. Let's say X belongs to M. Then its stabilizer is, let's say, denoted as Gx. This is stabilizer of X in G. Then it said that X and Y, two elements in M, are of same orbit type if gx and gy are conjugate in G. So you define orbit type. So this is the word used in geometry, the same orbit type. So same orbit type. This means that gx conjugate to gy in G. So I want to point out this theorem of Mostow. It's this, that if I have a, this is theorem. If I have a compact D group acting on a compact manifold, then there are only finitely many orbit types. Finitely many orbit types. So this is, later you realize that why I am interested in finitely many kind of things. That's one of my interests to look at here. Just as an example, if I take, let's say, orthogonal group, compact orthogonal group, Y and R, acting on, I can just think of maybe, let's say, Rn, even though it's not compact. So what are the orbits here? How do they look like? So the orbit, of course, I can take 0 will form just one orbit. And what else? Students. So if I take an element, let's say element of a particular length, x has some length, norm x, then if I apply an orthogonal group element, it will just norm. So it will form basically a sphere, but a sphere of radius norm x. So it will basically form concentric spheres. That's what are going to be orbits here. And they are all kind of homeomorphic to each other. So they're same orbit type. So if you look at the stabilizer of an element here, it is just ON minus 1. And it is going to give you same orbit type. Okay, so another motivation for me is, this is what you already saw earlier in the lectures from representation theory. And we had seen earlier character table of group maybe SL2Q or GL2Q. If you look at the character table of GL2Q, you see that many conjugacy classes are grouped together, and the representations or rather characters are also grouped together. And that grouping is grouping of characters is kind of related to G classes. This was this is noted by Green in the paper on GL and Q representation theory. So that's another interesting motivation. And of course, this is important problem in representation theory. I think in the lectures of Professor Gerard, we saw this importance of conjugacy classes and computing centralizers and their conjugacy. Okay, so third thing is for me is this theorem of Steinberg. Steinberg's theorem. So let me define. So let me get back to my the main question, which I have not said what is the main question, because in my title there is something to do with algebraic groups. So the kind of groups I am interested in here, the algebraic groups. So algebraic groups is, let's say, first we fix a field K, algebraically closed field. Then algebraic group is supposed to be an affine. So I'll look at only affine algebraic groups, affine variety, and it has group structure, and it's also a group. It has a group structure, and the multiplication map sends xy to xy, and the inverse map. These are also morphism of varieties. And there is more general notion of groups defined over any field K. So I will have algebraic group G defined over more general field K, where K need not be literally closed. And I have its K points, which is denoted as G of K. So for example, you can keep in mind the group GLN or SLN. These are algebraic group, and the K point of this is actually what you write as a GLN K. So that's the notation for this. And there are other examples. For example, you can look at orthogonal groups, symplectic groups. We have seen many groups. We have seen groups G2, F4. All these things we have seen already. So these are examples of algebraic groups. Okay, so here's a question. So the question is, now the earlier question what I had asked is parameterize G classes in algebraic groups. I'm going to be interested in, let's say, reductive groups. So there is an interesting theorem of Steinberg, which is what I wanted to point out here. Theorem of Steinberg is that if I take G connected reductive algebraic group, this is over algebraically closed field. I'll just write it in the bracket. And suppose characteristic of G is good, then there are finitely many G classes. So this is quite interesting theorem. So for example, let's look at the group GLN. So GLN, if you look at conjugacy classes, there are infinitely many conjugacy classes, whereas this theorem says there are only finitely many Z classes. So that's the importance of this theorem. So more precise question is this, that which we are trying to solve right now, is this, that so can we generalize this theorem of Steinberg in the sense that this theorem is for algebraically closed field. Can we make similar statement for base field? When can we say there are finitely many G classes? So for what K GK has finitely many G classes. That's one. And as we know from infinite group theory and representation theory, it's important to count these numbers. Can we count? So when it is finite, count the precise number. Count the number. So these are the questions which we are trying to answer. So let me tell you some cases where this has been done so far. So okay, so I'm just going to phrase differently the answer. So for that, first I will define this what I called fields with property Fe. What are these fields? K has property Fe. If first of all it's perfect, and it has only finitely many extensions of any given degree of any finite degree. So this is certain kind of fields. These fields are very interesting. So for example, I mean there are nice fields belong to this kind of thing. So for example, of course, any algebraically closed field. So you can think of C, real numbers, finite fields, local fields, all these kind of fields belong to this class. Okay, so here is some work done. So suppose I have, so first, this is work of Ravi Kulkarni, 2008. GL and K has finitely many G classes. If K is Fe. This can be also checked using Jordan canonical form, if you know, basically. So around that time, I was looking at groups of type G2. G2, and this also has finitely many G classes. G classes. Again, with the hypothesis, K is Fe. After this, Krishnendu Gangopadhyay and Kulkarni. There is this for orthogonal and symplectic groups. This is 2014. That it has finitely many G classes if K is Fe. Recently, we extended this to unitary group. This is work of my student, Sushil Bhunia and So this is same holds for unitary group. Okay. And now we believe that maybe this result can be proved for in general for reductive group, though it didn't seem, I mean, okay, we are still stuck at some point. The method in all this proof is basically explicitly writing down centralizers, and then you note down at the end that it will be only finitely many G classes if you have that hypothesis on K. Related work I want to mention, maybe you have seen already the posters. Genus number. There is a poster by Anupam. So genus number is essentially G classes. It's just a term used in Lie theory basically. And he has computed genus number for compact Lie groups and more general connected, simply connected algebraic groups or algebraically closed field. Okay, so I give you example where it holds true, and then you'll be wondering that why that kind of hypothesis. Once we have counterexamples, so counterexamples are very easy. So this is example. We'll think of the smallest example, GL2Q, and it has infinitely many G classes because Q doesn't satisfy, of course, that property, and you can embed any degree 2 field extension of Q inside this as a centralizer, and that will say that there are infinitely many G classes here. So, and of course you can use this to cook up example in other groups also. So kind of hypothesis is necessary in a way. Okay, so I also wanted to write down I still have 17 minutes. So let me write down some counting results, what we have got, and then I'll come back to give you a bit of sketch of the proof. So here are some counting results. For finite field. So, okay, for notation, Pn is basically partitions, number of partitions of n, and the generating function for Pn is given by 1 by, so product of 1 by 1 minus x to the power I equal 1 to infinity. So that's just for notation. So here are some formulas for GLN. So for GLN, this has been kind of known. So number A. So let me, okay. So GLN. So I'm going to write the generating function for number of G classes that I'm going to denote by ZX. This is for the group GLN. So ZX is going to be, let me first define what is ZX. ZX is given by this formula, I equal to 1 to infinity, 1 divided by 1 minus x to the power I, and whole power partition function, P of I. So the result is this, that if I want to count for algebraically closed field, no matter what, K equal to K bar, it's this function here, Zx. And if I want to count over reals, remember over real, there is a degree 2 field extension. So want to count this over real, then this is going to be zx and zx square. Any algebraically closed field, so I put k equal to k bar. Yeah, the same number is zx. And for finite field, this formula is there in Green's paper, and we just write it differently here using our this notation. So zfqx is product of zx to the power I equal to 1 to infinity. So somehow this formula reflects arithmetic property of the field, where I'm writing generating function, so it's a function. So the coefficients are the number. So this is very interesting, that it somehow reflects the arithmetic property of the field here. For unitary group, so we counted for unitary group or finite field especially, which is what is more important. So for U and Q, so here is the theorem. That is, so if you take Q bigger than N, then number of G classes in UN, Q is same as number of G classes in GLN. That is quite interesting. Okay, so I'll now go back and try to sketch proof for unitary group. So let me first begin with defining a general unitary group. To define a general unitary group, I begin with a field extension of degree 2 with a yellow automorphism. Let's say sigma. This is a degree 2 extension, and the automorphism is given by sigma. And we'll also, for simplification, sigma is denoted as R. And we have, let's say, a vector space V over K of degree N, dimension N. And I have a Hermitian form B. Over V. So Hermitian form is basically a map from V cross V to K, which is linear in first coordinate and bar linear in second coordinate. We'll also assume that this is non-degenerate. Right? Then the unitary group is nothing but isometries of V comma B. So unitary group is nothing but all linear transformations in GLV which preserve B. For all VW in V. For algebraically closed field, up to equivalence, there is only one Hermitian form. So there is one unitary group, so only one. No, for finite field, I want to say first. For finite field, there is only one Hermitian form. So there is only one group, that is what we denote by, up to conjugacy, there is only one group, U and Q. over algebraically closed field, there could be many. So for k equal to k bar, it's kind of related to quadratic forms. So let's say over complex number I want to say, over C. So the base field will be R. So the number of Hermitian form is related to the number of quadratic forms over R, which are given by alternating plus minus signature. Okay, so I don't want to write too many things. So okay, now we want to. So I want to just sketch the proof for finiteness of G classes in unitary group. BB in general. So there are three key steps. So the first thing what we do is that we use that every element has a Jordan decomposition. So I can write it as a product of semi-simple and unipotent. This is where we assume a perfect field. So I am using perfect field. Otherwise Jordan decomposition may not be true. And so let's say this is Jordan decomposition. So my element G belongs to the unitary group. Then we also know that these two elements commute. So if I want to look at the centralizer of this, okay, I'll write UVB as G. Centralizer of G will be given by intersection of the centralizer of this semi-simple and unipotent. Intersected with centralizer of G, which can be also, and it's a general theorem that this GU belongs to connected component of semi-simple centralizer. So this I can write as centralizer of GU in this subgroup, which is centralizer of GS in G. So it seems that if I want to calculate centralizer, I have to calculate basically this quantity, which essentially comes down to computing or completing rather these three main steps. So steps number one. So first we have to find these kind of groups, which are supposed to be centralizer of semi-simple elements. So describe centralizers of semi-simple elements. Yeah. And number two, check if these are finite, because I'm trying to prove finiteness. So I will use my hypothesis about K at this step here. And number three is going to be actually finding centralizer of unipotents inside these groups now. So centralizers. Sorry. Check these are finite up to conjugacy. Right. So third step is centralizers of unipotents in the groups you obtained at step one. In the groups obtained in step one. There has been a lot of work in computing conjugacy classes, especially in classical groups. These things have been very well described by many people. And we use parameterization from there, and then we compute centralizers. So first we use conjugacy classes description in classical groups. So there is work of Springer Steinberg and Wall and many people, MacDonald. So there is a lot of work. And so we use description of these conjugacy classes from here. And then we compute centralizers. So first should compute centralizer of semi-simple element. So this turns out that in this case, you can describe centralizers of semi-simple as a product of certain GLN K, which could be extension of, so let's say Ki, GLN I, and certain product of unipotents, unitary groups. Unitary groups are some other subspaces, Wi with some form HIs. But here the unitary group could be a little more general. This could be over also field of the kind K cross K or something. But that can be reduced to this. So ultimately you have only two kind of groups appearing. And again, this could be over bigger field. So this need not be over the base field little k. So it could be over some other, let's say Li over. So that actually kind of simplifies the work in step 3, because unipotents in GLN K are kind of understood. Then again you have to look at unipotents inside unitary group, and we understand conjugacy classes. So again, use that theory to understand centralizers, and we prove that finitely. Total finiteness comes because here we know already by earlier work that conjugacy class of centralizers are finitely many. This number of HIs will be restricted, because over such field there can be only finitely many Hermitian forms, because Hermitian forms are also given by number of forms depends on basically K star mod norm from K star, and this is finite because K star mod K star things are finite. So using that, there are only finitely many forms. So yeah, all this you use. So proving finiteness is a little bit easier because you don't have to actually compute exactly these numbers, but you have to describe this much more clearly if you want to actually count the number. So one has to be more precise than actually doing that. So one has to explicitly describe all these depending on element, and then look at its minimal polynomial, characteristic polynomial, exactly figure out how many components and which groups appear, and then get that. Okay, I'm 1 minute before, I will stop here. Okay.
Thank you very much for this nice talk. Are there any questions or comments?
Okay, that itself is a question we have not studied. All we are trying to use the property. So the way we use is that there could be, so if I have this field K with that property, K with Fe, so this means that K star mod A star square is finite, because there are only finitely many degree extensions, and of course there are finitely many higher degree extensions also. So one conclusion from this you can draw is that there are only finitely many quadratic forms. Which is used here, for example. You cannot have then infinitely many choices for these subgroups. So So this is how we are exploiting that property. We need full strength because any higher degree field extension you can embed inside GL and K as exactly. So if you have some field extension, then you can take irreducible polynomial and corresponding element you can embed, and that will be, yeah. So for GL and K itself, you use the full strength. But this is another way of using here. Which numbers? That is usually done only for semi-simple elements. So semi-simple centralizer classes are used in the linguistic theory. So they are generally computed, and they are yeah, right. So of course, if you look at only semi-simple, it will coincide. But we are counting also all G classes. For GLN, that's what is interesting.
Any other questions?
Right. Right. So so the definition is that you have to the definition is that Gx and Gy are conjugate in G. So I have to compute Gx and Gy. So what will be the stabilizer when acting on Rn? So yeah, so let's say is same. The group will be same, the stabilizer group. Yeah, stabilizers. Yeah. So even if I take the vector even or any scalar multiple, it will give me the same stabilizer. Okay, I don't know. I have not looked at in detail. I have only looked at the theorem. Okay. Right. Yeah. That is more, I think there are more general version of that theorem available where you put some more hypothesis on group than the manifold. For example, I think for toral group or something, there is a nice classification where you don't put any restriction on the manifold.
Are there any other questions or comments? No? Well.
Thank you.